Let's look at another application of the divergence theorem. Many times the use of the divergence theorem is very handy when the vector field is complicated, yet the divergence of the vector field is reasonable. So here's what we have in this problem. We've got a surface that's bounded by the following graphs. That is, the cylinder z equal 4 minus x squared, the plane z equal 5 minus y, and we have the xy plane, which is z equals 0, and the xz plane, which is y equals 0. Now, when you look at describing this as a solid, it's a lot easier to think of the xz plane as being the ground foundation, so to speak, because you can see that we move from y equals 0 to a very simple equation of y. If we solve for y equals 5 minus z, so we can be moving out in the positive y direction to make the description simpler. So as you project onto the z-axis, you get x running from -2 to 2, and then of course you get z running from 0 to 4 minus x squared here, and then as I noted before, y will run from 0 to 5 minus z. So this would be a very simple description of the solid Q that doesn't require lots of algebra. So now let's look at the vector field. We have a vector field. The first coordinate, or the m, is x cubed plus e to the minus y sine z. The second coordinate, or n, is x squared y plus the inverse tangent of z. And the third coordinate, p, is the square root of y times secant x. Now when we take the divergence of that vector field, we'll do an x partial here, and we get 3x squared. We'll do a y partial for this coordinate, and we just get an x squared. And then of course there's no dependence on z here, so the z partial is 0. So the divergence simplifies to 4x squared. So that's much more of a simplification than we would have thought when we looked at this problem. And so now when we consider the flux of f through the surface S, we write this as the surface integral here. And then, of course, by the divergence theorem, we replace it with the triple integral of the divergence of f over q. And so now what we can do is go ahead and fill in our limits. So we have -2 to 2, 0 to 4 minus x squared, and 0 to 5 minus z for the last variable y of the divergence 4x squared. Then, of course, we have dy, dz, dx. Now, when you look at this particular integram, it's only a function of x, and this is an even function, and the x interval is symmetric. So first, what we can do is we can factor the 4, and then we can replace the lower limit, -2, with 0, and multiply the result by 2, just using the even function integrated on a symmetric interval. So we're using our techniques as to start the problem from the triple integration, and now we're using a calculus 1 result, even in a triple integral. So this simplifies the result. And now, of course, for the y integration, there is no y independence here, so we simply just get the x squared times the y, and we just replace that with 5 minus z, the 0 lower limit giving us nothing to worry about. And so now we have the 8 times the new integrand, x squared times 5 minus z. Now we want to integrate with respect to z, but we have another calculus 1 integral. So we need to utilize the fact that by the chain rule we get a -1 here, so we're going to pay for that here with the -8 divided by 2. That is, when we add 1 divided by the new power, we get the -1/2. So we put this out to the left of the integral, and then we evaluate from 0 to 4 minus x squared. So again, very simple calculus 1 integrals, but I'm trying to make it as simple as I can as I neaten it up with each step. And so now we just need to evaluate, but notice the lower limit will give us something non-zero. So when we substitute 4 minus x squared, we're going to get a 5 minus 1, and the minus will be a plus x squared, which we have here, quantity squared. And then, of course, when we substitute 0, we get 5 squared, so we have the -25. Now, the last integration is x, so let's just go ahead and simplify here. This particular binomial here squared will be x to the fourth plus 2x squared plus 1. And then, of course, when we subtract 25, we'll get x to the fourth plus 2x squared minus 24. All of this times x squared. So we just need to do that simplification. And now let's distribute the x squared. We'll get an x to the sixth. We'll get a 2x to the fourth minus a 24x squared. Now, again, very simple integrals. Add 1, divide by the new power. So we have the -4 coefficient from the left. So we have x to the 7th divided by 7. And then, of course, here, 2x to the 5th divided by 5. And then, of course, we have the add 1 divided by the new power. We're going to get an x cubed divided by 3. But the 3 will absorb into the -24 to give us a -8. So now, of course, we just need to evaluate, observing that the lower limit zeros the antiderivative. So now let's just go ahead and substitute the 2. So we have a -4, so we'll get 2 to the 7th, and we'll get 2 times 2 to the 5th, which is 2 to the 6th. And of course here we have an 8, which is 2 to the 3rd, times 2 to the 3rd is 2 to the 6th. So I went ahead and looked at the algebra this way because I think it's a little bit simpler. And then, of course, it's easier just to go ahead and factor all these common powers of 2, which is 2 to the 6th times the -4 that's already out to the left. And then, of course, that leaves behind 2 over 7, a 1 over 5, and then, of course, I'm going to need a common denominator of 35 here, so I'm going to write that -1 as 35 over 35. And then finishing the common denominator, and of course, observing here, 2 to the 2, 2 to the 6, that'll give me the -2 to the 8. I'll have a 10 plus a 7 with the common denominator for the first two terms, and when I subtract the -35, I get a -18. So now what you see is we have a negative times a negative, which is a positive, and 18 is 2 times 9, so that's going to give us 9 copies of 2 times the 9. But of course, 2 to the 9th is something we know. That's 256 times 2, which is 512, and 512 times 9 will give us 4,608 with a denominator of 35. So here we do necessarily see the power of the divergence theorem. Trying to compute a surface integral with a really complicated vector field like this would be a daunting task. So we see these vector calculus theorems do introduce very elegant techniques to push through computations of surface integrals that would otherwise be very difficult. And we are done.